Welcome to Securing Network Infrastructure. I am Dr. Ala Jabbar Al-Maliki. Welcome to the Universiti Utara Malaysia School of Computing. Every digital interaction we perform relies on an invisible foundation, the network infrastructure. This visualization shows the massive scale of modern systems, where local hubs route data across global exchanges. These nodes are the backbone of modern communication. However, these systems were built with an inherent paradox. Historically, network architecture was designed to share information as efficiently as possible, prioritizing openness over restriction. Because the priority is frictionless connectivity, these systems remain vulnerable to exploitation. By default, the network is an open door for malicious actors. Protecting this infrastructure requires us to analyze the models they are built on, identify specific vulnerabilities, and engineer defenses into the very fabric of the network. We start with the physical scale of the network. A local area network, or LAN, connects devices in a confined space, like a campus, using switches. A wide area network, or WAN, uses routers to bridge those LANs across entire cities or countries. The shift toward wireless networks removed physical cables entirely. This increased flexibility, but it also removed the physical boundaries that once helped contain network traffic, expanding the attack surface. To standardize how data moves across these devices, we use the OSI model. These 7 layers define exactly how information is formatted and transmitted. While the OSI model is the theoretical standard, actual implementations use the more condensed TCP/IP model, which maps these functions into 4 practical layers. Data travels through specific critical points: Layer 7 for the application, Layer 4 for transport, and Layer 3 for network routing. These models ensure communication works, but they assume the traffic is legitimate. Without additional security controls, every layer is an opportunity for an attacker to intercept or manipulate data. The openness of these protocols allows for specific attacks aimed at compromising the confidentiality, integrity, or availability of data. Eavesdropping, or packet sniffing, is a passive attack. Here, an unauthorized entity silently captures sensitive data as it moves across the network. In a man-in-the-middle attack, the threat is active. An attacker intercepts the stream, reads the contents, and can modify the data before it reaches the intended recipient. These interceptions are particularly common on public, unencrypted Wi-Fi networks, where there are no physical barriers to stop an attacker from seeing your traffic. Other attacks target availability. Denial of service and distributed denial of service, or DDoS attacks, focus on making a system unusable. A DDoS attack overwhelms a server with a flood of malicious traffic. This blocks legitimate users and often results in massive financial and operational losses. These attacks succeed because traditional networks are built to trust the traffic they receive. To stop them, we have to move away from a model of implicit trust. A single security barrier is no longer enough. We must implement defense in depth, where multiple security layers work together to protect the internal network. The firewall is the primary boundary. It filters incoming and outgoing traffic based on security rules, using stateful inspection to distinguish between legitimate and malicious requests. To catch threats that bypass the firewall, we use an intrusion detection system. This internal watchman monitors the network for suspicious activity and alerts administrators to potential breaches. An intrusion prevention system goes a step further by actively terminating those malicious connections to stop an attack in progress. For remote access, virtual private networks create encrypted tunnels. This ensures that even when data travels over public infrastructure, it remains hidden from eavesdroppers. Network segmentation adds another layer of protection. By isolating different parts of the network, we ensure that if one zone is compromised, the attacker cannot easily move to other sensitive areas. These tools lead us towards a new philosophy: zero-trust architecture. In this model, we move past the idea of a safe internal network and enforce the principle of least privilege. In a zero-trust environment, trust is never assumed based on a user's location. Every device, user, and packet is continuously verified before access is granted. These architectural defenses only work if they are supported by strong cryptographic protocols. HTTPS and SSL/TLS provide the necessary encryption for web applications, ensuring that data moving between a browser and a server cannot be read by others. For remote system management, Secure Shell provides a protected channel, while IPsec secures communication at the network level itself. Managing these protocols across a large organization requires adherence to international standards to ensure consistency and reliability. Standards like ISO IEC 27001 and the NIST Cybersecurity Framework provide the guidelines needed to implement and manage these security practices effectively. While protocols provide the technical encryption, these standards provide the organizational structure required to maintain a secure environment over time. This node represents our goal, an infrastructure where every data packet is verified and every connection is encrypted. Securing a network is an ongoing architectural discipline. It requires moving beyond simple software solutions to build security into every layer of the system. This involves understanding network models, deploying layered defenses, and consistently using secure protocols. Thank you for your time and attention during this lecture. Mastering these technical and organizational layers is a foundational skill for anyone entering the cybersecurity profession today.